In this video, we'll explore the asymptotes of rational functions. If p of x and q of x are polynomials, where q of x does not equal 0, then p of x divided by q of x is a rational function. The domain is all real numbers, except of course where q of x equals 0. An example is f of x equals 1 divided by x minus 1 squared. So here I can't factor this, but I would say the domain is everything except 1. It cannot equal 1, can it? So it'll have to be negative infinity up to positive 1, union indicating it can't include 1. Also that is indicated by the parentheses. Now, in order for me to find the domain of g of x, I would have to factor g of x. So when we factor g of x, we see that it becomes 4 of x divided by two linear factors, x plus 4 and x minus 2. So that means x cannot equal negative 4. So the domain would be everything except negative 4 and positive 2. So this is how we write the domain as everything except negative 4 and positive 2, because we cannot divide by 0. A word about notation. We write x with an arrow pointing to c with a plus above it, and that means x is approaching c from the right. It never equals c, but it comes in very close. X with an arrow, c with a negative sign in the superscript means x approaches c from the left. It comes in from the left, but it never equals c. X approaches negative infinity and x approaches positive infinity. These mean x decreases or increases without bound. In the example, we're given f of x equals 1 divided by x minus 1 all squared. What happens to the y values, the f of x values, as we approach 1 from the left, and what happens to those y values as we approach 1 from the right? So as we consider the graph of this function, as we approach the value x equals 1 from the left, so x equals negative 3 and x equals negative 2, as we get to x equals 0, we see y, f of x equals 1. Then we go up to x equals 1/2, y equals 4, x is about 3/4, y equals 16, and the closer we get to 1 from the left, the closer y, f of x, is to positive infinity. So as x gets closer and closer to the number 1 coming in from the left, f of x, the y value, approaches positive infinity. We can never say x equals 1 because then we're dividing by 0. So if we approach the number 1 from the right, so x is 7, x is 6, x is 5, etc., we get to x is 2, y is 1, and then we get to x is about 1.5, y is 4, 1.25, it goes up to 16, and then as we get closer and closer, it goes to positive infinity. 1.01, it's 10,000, 1.001, it's 1 million, and it goes to positive infinity. So again, for this example, as we approach the x value positive 1 from the right, the y values f of x go to positive infinity. We can never say x equals 1 because then we're dividing by 0. The vertical asymptote of a rational function. If we have a rational function where f of x equals px divided by qx, qx can't be 0, and p of x and q of x have no common factors other than 1. If c is a 0 of the denominator q of x, then the line, the vertical line x equals c, is a vertical asymptote of the graph of f of x. So in the case of our example, the vertical asymptote is x equals 1, because that's the place where the denominator is 0. We have a vertical asymptote at x equals 1. We want to find the vertical asymptote or asymptotes of g of x, which equals 4x divided by x squared plus 2x minus 8. So we have factored this before. It equals 4x divided by the linear factors x plus 4 multiplied by x minus 2. So the zeros of the denominator are when x equals negative 4 and when x equals positive 2. And if we graph g of x, we'll see x equals negative 4 here as a vertical asymptote, and x equals positive 2 here is a vertical asymptote. A vertical asymptote occurs at any values that make the denominator 0. Horizontal asymptotes, if we're given the rational function a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 plus, keep going, plus a sub 1 x plus a sub naught, all divided by b sub n x to the power n plus b sub n minus 1 x to the m minus 1 plus dot 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 plus b sub 1 x plus b sub naught, we may have horizontal asymptotes or we may not. If the degree of the numerator equals the degree of the denominator, n equals m, then the horizontal asymptote is the line y equals a sub n over b sub n. If the degree of the numerator is less than the degree of the denominator, n is less than m, the line y equals 0, which is the x-axis, is the horizontal asymptote. But if the degree of the numerator is greater than the degree of the denominator, n is greater than m, there is no horizontal asymptote. So let's reconsider the example we've already looked at. G of x is 4x all divided by x squared plus 2x minus 8. And we found the vertical asymptotes, x equals negative 4 and x equals positive 2. Now, there are horizontal asymptotes. The degree of the numerator, n, is equal to 1, isn't it? And the degree of the denominator, 2, is equal to m. Since n is less than m, the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is the line y equals 0, which is the same as the x-axis. So we previously found the vertical asymptote x equals negative 4, and we found the vertical asymptote x equals 2. Now the horizontal asymptote y equals 0, and you can see that the graph is asymptotic. It gets arbitrarily close to the line y equals 0, the x-axis, going in the positive x direction and also going in the negative x direction. It gets arbitrarily close. In this problem, we're asked to find the vertical and horizontal asymptotes if any of s of x equals 4x plus 16 in the numerator, x cubed plus 2x squared minus 8x in the denominator. So in order to do that, we'll have to factor. So in the numerator, I have 4 times x plus 4. In the denominator, I can factor out an x. So I'll get x, and then I'll get x squared plus 2x minus 8. I can continue to factor that. So I have 4x plus 4 all over x plus 4, x minus 2. And I can see that I have a common factor in the numerator and the denominator. So that's actually multiplying everything by 1. So this simplifies to 4 all over x minus 2. But I can't ignore the fact that I had this factor of x plus 4. So my vertical asymptotes are everywhere the denominator is 0. So that's x equals 0, x equals negative 4, and x equals positive 2. So they're all the places where the original denominator is 0. When I graph this, I'm going to have a hole in the graph. And that hole will occur when x is negative 4 and y is 1/6. For my horizontal asymptotes, the degree of the numerator is 1 and the degree of the denominator is 3. So that's going to be the x-axis, or y equals 0. And here's our graph. Our vertical asymptotes, x equals positive 2 and x equals 0. And our horizontal asymptote, y equals 0, the x-axis. And notice there is a hole at the point negative 4, 1/6. In this example, we want to find the vertical and horizontal asymptotes, if any. F of x equals 2x squared plus 1 all over 3x cubed. Vertical asymptotes are easy. That's where x equals 0, because that's where the denominator is 0. Since the degree of the numerator is 2 and the degree of the denominator is 3, 2 is less than 3, that means our horizontal asymptote is y equals 2 divided by 3, the leading coefficient of the numerator and the leading coefficient of the denominator. So here's our graph. Here's our vertical asymptote, x equals 0, or the y-axis, and our horizontal asymptote, y equals 2/3. A graph simply cannot cross a vertical asymptote, but it might, or it might not, cross a horizontal asymptote. So we want to find where the graph crosses the horizontal asymptote. Because the degree of the numerator is 2 and the degree of the denominator is 2, we know the horizontal asymptote is y equals 6 divided by 3. So the horizontal asymptote is y equals 2. If I want to find the point where the graph crosses the horizontal asymptote, I would solve 2 equals 6x squared minus 18x minus 8 divided by 3x squared plus 1. So that gives me 2 times 3x squared plus 1 equals 6x squared minus 18x minus 8. 6x squared plus 2 equals 6x squared minus 18x minus 8. I can subtract 6x squared from both sides, and I will get 10 equals negative 18x, or in other words, x is equal to minus 5/9. So the point where it crosses the axis will be x is minus 5/9 and y is 2. So here's my graph. So the horizontal asymptote is the line y equals 2, and the graph crosses at the point minus 5/9, 2. Sometimes a rational function has a slant asymptote. This happens when the degree of the numerator is 1 more than the degree of the denominator. In our example, we're asked to find all the asymptotes of f of x equals, in the numerator, x squared plus 3x plus 2, and in the denominator, x minus 3. So if I want to find all the asymptotes, I'll start with the vertical asymptotes. The denominator is 0 when x equals 3, so that's my vertical asymptote. Next, I'll consider horizontal. There are no horizontal asymptotes because the degree of the numerator is more than the degree of the denominator. There is a slant asymptote. The degree of the numerator is 1 more than the degree of the denominator. So the way to find my slant asymptote is I have to divide the denominator into the numerator. Now I can do this using long division, or I can do this using synthetic division. Synthetic division is faster, so I'm going to use that. So bring down the 1. 1 times 3 is 3. 3 plus 3 is 6. This is 18. 20, so it doesn't go in perfectly, but it does not matter because this is x plus 6 here. So my slant asymptote is y equals x plus 6. I don't consider the remainder when I look at the slant asymptote. So here's the graph of my function f of x, and here's the slant asymptote. Finally, if the degree of the numerator is greater than 1 more than the degree of the denominator, the end behavior is just governed by the leading terms. To illustrate this, let's consider the function x to the power 4 plus x squared plus 1 divided by x minus 1. The leading terms are x to the power 4th divided by x, so the end behavior is really governed by that.